Welcome. Today, we're diving into the world of Java multithreading and collections. Multithreading is a powerful feature in Java that allows programs to execute multiple parts concurrently, making applications more responsive and efficient. We'll explore the advantages, how threads are created, and key differences between common Java data structures. Whether you're preparing for an interview or brushing up your skills, this video will guide you through essential concepts with clear explanations and practical examples. Let's get started by understanding why multithreading is so valuable in modern Java applications. Multithreading brings several advantages to Java applications. First, it enhances responsiveness, especially in interactive applications, by allowing code to run even when certain sections are blocked or executing lengthy processes. Threads can share resources, perform message passing, and use shared memory, making processes more economical. Scalability is another benefit, as multithreading increases parallelism on multi-CPU machines. Thread synchronization functions also improve inter-process communication, and overall, system resource usage is minimized. These features make multithreading a cornerstone of efficient and scalable Java programs. In Java, there are two main ways to create a thread. The first is by extending the thread class. You simply create a new class that extends Java, lang, thread, and override its run method. The second way is by implementing the runnable interface. Here, you create a class that implements runnable and override the run method, then instantiate a thread object and call start. Both approaches allow you to define the code that should run in parallel, but using runnable is often preferred for flexibility, especially when your class needs to inherit from another class. A thread in Java is a lightweight subprocess, representing the smallest unit of execution within a process. Each thread has its own program counter, execution stack, and local variables, but shares memory space with other threads in the same process. This means threads can operate independently, and if one thread encounters an exception, it doesn't affect others. Java supports multithreading through the thread class and the runnable interface, making it easy to write concurrent programs that are both efficient and robust. Processes and threads are both units of execution, but they differ in several ways. A process is a program in execution, with its own memory space and resources. Threads, on the other hand, are sequences of instructions within a process and share the same memory. Threads are faster to create and terminate, and context switching between threads is quicker than between processes. Communication between threads is more efficient, but they must be carefully synchronized to avoid issues. Understanding these differences helps in designing efficient, concurrent applications. Thread in Java goes through several states during its life cycle. It starts in the new state when created but not yet started. Once started, it enters the runnable state, where it's ready to run or is running. If it's waiting for a resource, it moves to the blocked state. The waiting state occurs when a thread waits for another thread's action or a specified time to elapse. Finally, the thread enters the terminated state after completing its task or being stopped. Understanding these states is crucial for managing thread behavior in your application. The sleep method in Java temporarily pauses the execution of the current thread for a specified period. During this time, the thread enters a timed waiting state but retains any locks it holds. Once the sleep duration ends, the thread becomes runnable again. This method is useful for simulating delays or managing timing in concurrent applications. For example, you might use sleep to pause a thread for 1 second in a loop, allowing other threads to execute and improving overall program responsiveness. In Java, the main thread is the entry point of every application. It's automatically created when the program starts and executes the main method. The main thread is responsible for running the core logic and handling user input. As the parent thread, it can spawn additional child threads to perform concurrent tasks. Managing the main thread and its children is essential for building responsive and efficient Java applications. Daemon threads in Java are low-priority threads that run in the background to perform tasks like garbage collection or signal dispatching. Unlike user threads, daemon threads do not prevent the JVM from exiting. They stop automatically when all user threads finish. Daemon threads are ideal for background tasks that don't require explicit shutdown, making resource management simpler and more efficient. Threads in Java can enter a waiting state in several ways. The sleep method pauses execution for a set time, while the wait method suspends a thread until another thread notifies it. The join method causes a thread to wait until another thread finishes. Threads may also wait for I/O operations or become blocked due to synchronization issues. Managing these waiting states is crucial for building robust, concurrent applications. On a single CPU, Java simulates multithreading using time sharing, also known as time slicing. The operating system rapidly switches between threads, giving the illusion of parallel execution. Java provides synchronization and locking mechanisms to prevent issues like race conditions. While this approach enables multitasking, true parallelism is only possible on multi-core systems. Still, time-sharing allows efficient use of CPU resources. Java threads have priorities ranging from 1 to 10. The JVM assigns a default priority called norm priority. Other options include min priority and max priority. Thread priorities help the scheduler decide which thread to run next, but they don't guarantee execution order. Proper use of priorities can improve application responsiveness, especially in complex, multi-threaded programs. Garbage collection is essential in Java to prevent memory leaks and ensure efficient memory usage. The JVM automatically manages memory by removing objects that are no longer referenced. This allows developers to focus on application logic rather than manual memory management. Garbage collection makes Java applications more stable and less prone to crashes caused by memory issues. While garbage collection offers many benefits, it also has drawbacks. The main issue is that it can cause pauses in application execution, slowing down performance. Garbage collection is non-deterministic, making it hard to predict when it will occur. This unpredictability can lead to inconsistent application behavior. Additionally, frequent creation and disposal of short-lived objects can increase memory usage. JVM uses different types of garbage collection. Minor garbage collection, also called young generation collection, reclaims memory from short-lived objects. Major garbage collection, or old generation collection, handles long-lived objects that survive multiple minor collections. Full garbage collection reclaims memory from all generations and usually takes longer, causing temporary application pauses. Understanding these types helps optimize Java application performance. You can identify minor and major garbage collections in Java by enabling garbage collection logging with options like XX, print GC details. Minor collections typically print GC, while major collections print full GC. This information helps developers monitor and optimize memory management in their applications, ensuring efficient resource usage and better performance. A memory leak occurs when objects are no longer needed but still have active references, preventing the garbage collector from reclaiming memory. This often results from unclosed resources or retaining references longer than necessary. Memory leaks can degrade performance or even cause application failure, making proper resource management essential for robust Java programs. Java util regex package provides classes for working with regular expressions in Java. The pattern class defines patterns, while the matcher class performs match operations on text. Pattern syntax exception indicates syntax errors in regular expressions. Additionally, the matchResult interface represents the result of a match operation. These tools make string searching and manipulation powerful and flexible in Java. To validate a password in Java, you can use a regular expression that enforces specific rules. For example, a password must start with an alphabet, contain alphanumeric characters, and be 8 to 20 characters long. The regex checks for at least one digit, one lowercase letter, one uppercase letter, one special character, and no whitespace. This ensures strong, secure passwords for your applications. JDBC, or Java Database Connectivity, is a standard API that connects Java applications to relational databases. It provides classes and interfaces for sending requests, executing SQL queries, and retrieving data. JDBC consists of components like the JDBC API, Driver Manager, Test Suite, and JDBC ODBC Bridge drivers. This framework enables seamless communication between Java programs and databases. A JDBC driver is a software component that enables Java applications to interact with databases. It implements the JDBC API for a specific database management system, allowing connections, SQL execution, and data retrieval. There are 4 types of JDBC drivers: JDBC ODBC Bridge, Native API, Network Protocol, and Thin Driver. Choosing the right driver ensures efficient database communication. To connect a Java program to a database, follow these steps. Import the necessary packages, load the drivers using forName, register the drivers with Driver Manager, establish a connection using the connection class, create a statement, execute the query, and finally, close the connection. These steps ensure a reliable and efficient link between your application and the database. The JDBC API provides various methods and interfaces for easy communication with databases. It includes packages like java.sql and supports both Java SE and Java EE environments. This API enables the write once, run anywhere capability, making Java a versatile choice for database-driven applications. The JDBC connection interface allows Java applications to interact with databases. It manages the connection lifecycle and requires specific drivers for each database. By using this interface, developers can execute SQL statements and manage transactions, ensuring reliable and secure data operation. The result set interface in JDBC stores data retrieved from the database. It allows you to iterate through results using the next method and update data with updateXXX methods. The cursor starts before the first row, making it easy to process query results sequentially in your Java application. The JDBC row set provides a tabular way to store and manage data. It maintains a connection to the data source throughout its lifecycle and comes in 5 types: JDBC row set, cached row set, web row set, filtered row set, and join row set. Row sets offer flexibility for handling data in various scenarios, from simple queries to complex data manipulation. The JDBC Driver Manager class acts as an interface between users and database drivers. It creates and manages connections, keeps track of available drivers, and helps establish the correct connection for your application. Driver Manager also registers and deregisters driver classes, ensuring smooth database interaction. Iterable and iterator are both used for traversing collections in Java, but they serve different purposes. Iterable provides a way to iterate over a sequence of elements, typically using the iterator method. Iterator, on the other hand, helps in sequentially accessing elements with hasNext and next methods. While remove is optional in iterable, it's required in iterator. Common examples include list, queue, and set for iterable, and list iterator or enumeration for iterator. Lists and sets are both collection types in Java, but they have key differences. Lists are ordered and allow duplicate elements, accessed by index. Sets are unordered and do not allow duplicates, accessed by hashcode. Lists can store multiple null elements, while sets allow only one null element. Examples include array list and linked list for list, and hash set or tree set for set. A list allows duplicate elements and maintains insertion order, while a map does not allow duplicate keys and does not guarantee order. Lists can store multiple null elements, whereas maps allow only one null key but multiple null values. Lists use the get method for indexed access, while maps use key-based access. Examples include array list for list and hash map or tree map for map. Queues and stacks are both data structures for storing elements, but their operations differ. Queues use FIFO, first in first out order, with insertion at the rear and deletion at the front. Stacks use LIFO, last in first out order, with both insertion and deletion at the top. Queues are ideal for sequential processing, while stacks are used for recursion problems. Priority queue and tree set are both used for storing elements, but they have distinct characteristics. Priority queue allows duplicate elements and is implemented by the priority queue class, using a queue as the underlying structure. Tree set does not allow duplicates, is implemented by the tree set class, and uses a set as the underlying structure. Priority queue was introduced in JDK 1.5, while tree set came in JDK 1.4. A singly linked list contains 2 segments, data and a link to the next node, allowing traversal only in one direction. A doubly linked list has 3 segments, data and 2 pointers, enabling traversal in both directions. Singly linked lists use less memory and are simpler, while doubly linked lists require more memory but allow easier insertion and deletion at both ends. Failfast and failsafe are 2 approaches for handling concurrent modifications during iteration. Failfast collections throw a concurrent modification exception if modified during iteration, making them suitable for single-threaded environments. Failsafe collections create a copy for iteration, allowing modifications but with slower performance, and are used in multi-threaded environments. HashMap and TreeMap are both key-value pair collections but differ in implementation and behavior. HashMap uses a hash table and does not maintain order, making it faster for retrieval. TreeMap uses a red-black tree, maintains natural ordering based on keys, and is slower due to tree traversal. HashMap uses equals for key comparison, while TreeMap uses compare to. A queue is a linear data structure where elements are inserted at the end and removed from the front, following FIFO order. A deck, or double-ended queue, allows insertion and removal from both ends. Queues are used for waiting lists, while decks are useful for implementing stacks or handling elements from both ends efficiently. HashSet and TreeSet are both implementations of the set interface but differ in ordering and null handling. HashSet is unordered and allows null elements, while TreeSet is ordered based on natural ordering and does not allow nulls. HashSet is implemented by the HashSet class and TreeSet by the TreeSet class. Choose based on your need for ordering and null support. We've covered a wide range of Java interview topics, from multi-threading and thread management to collections and their differences. Understanding these concepts is crucial for building efficient, scalable, and robust Java applications. Whether it's managing threads, handling memory, or choosing the right data structure, these fundamentals will help you excel in both interviews and real-world projects. When working with Java threads and collections, always consider the specific requirements of your application. Use thread synchronization to avoid race conditions, and choose the right collection type based on ordering, duplication, and performance needs. Proper resource management and understanding of garbage collection will help you write reliable and efficient code. Interviewers often ask about the differences between processes and threads, how to create threads, and the advantages of multithreading. Be prepared to explain garbage collection, memory leaks, and the distinctions between various collections like list, set, map, and their implementations. Clear, concise answers demonstrate your understanding and readiness for Java development roles. Adopt best practices such as using thread pools for managing multiple threads, leveraging synchronized blocks for shared resources, and regularly profiling your application for memory leaks. Choose the most suitable collection based on your use case, and always close database connections to prevent resource leaks. These habits lead to more maintainable and high-performing Java applications. As you advance in Java, you'll encounter topics like concurrent collections, advanced thread synchronization, and custom garbage collection tuning. Understanding these advanced concepts will help you tackle complex, high-performance applications and prepare you for senior development roles. Keep exploring and practicing to deepen your expertise. Continue your learning journey. Explore official Java documentation, online tutorials, and open-source projects. Practice coding problems on platforms like LeetCode or HackerRank, and participate in Java communities for peer support and knowledge sharing. Continuous learning is key to mastering Java and staying updated with the latest developments. Thank you for joining this comprehensive overview of Java threads and collections. By mastering these concepts, you'll be well equipped to build robust, efficient, and scalable Java applications. Keep practicing, stay curious, and apply these principles in your projects and interviews. Good luck on your Java journey. This brings us to the end of our video. Remember, understanding threads, memory management, and collections is fundamental for any Java developer. Review these topics regularly and apply them in your coding practice. Thanks for watching, and see you in the next video.